Hello, everyone. I'm Rafael Hidalgo, and I'm pleased to present our project developed with Jesse Perrone, Dr. Parna Varde, and Dr. Wei-Tien Wang. Our project, the Robo-CSK-Organizer system to optimize machine learning and autonomous grasping, focuses on enhancing robotic systems by integrating common sense knowledge. This integration improves robotic perception capabilities and the explainability of decisions made by robots. Also, after our presentation, we will show you a brief video demonstration. In recent years, multi-purpose robots have evolved from performing simple tasks to managing complex operations in various domains, including manufacturing, healthcare, and domestic environments. However, traditional robots, especially those using deep learning, often operate as opaque boxes, making their decision-making processes unclear, which is problematic in dynamic settings where nuanced decisions are essential. Our project addresses these challenges by enhancing the explainability and adaptability of robotic systems. We realize that integrating common sense knowledge, basic everyday understanding that AI lacks, into robotics could significantly improve their ability to make more informed and contextually appropriate decisions. The Robo-CSK-Organizer system is our solution. By incorporating the ConceptNet knowledge base, along with advanced tools like DETIC for object detection and BLIP for context recognition, we developed a system that enhances decision-making and ensures the process is transparent and understandable for users. This project paves the way for smarter, more versatile robotic applications that can operate reliably in dynamic environments, advancing AI-driven robotics. Our approach, the Robo-CSK-Organizer, is a major advancement in robotics designed to demonstrate explainable AI by integrating common sense knowledge. The goal is to enhance the decision-making capability of robots, making them more intelligent, adaptable, and transparent. At the system's core is the ConceptNet knowledge base, which provides everyday reasoning that helps the system make decisions that are accurate and understandable. One key challenge in AI is the opaque box issue, where decisions are hidden and hard to interpret. Robo-CSK-Organizer tackles this by offering clear, explainable insights into reasoning, ensuring that robot actions are effective and transparent, thereby building trust in human-robot interactions. This block diagram shows the core components and data flow in Robo-CSK-Organizer. The core AI module at the center orchestrates interactions between components. On the left, ConceptNet provides essential background knowledge, while user-guided queries tailor the system's responses to specific tasks. In the center, robotic hardware integration includes the Frank Amica robotic arm and Intel RealSense Depth camera, both managed by the robot operating system for seamless control. On the right, data flow and integration cover how the system processes information. Integration with BLIP and DETIC enhances object detection and context recognition, leading to accurate scene interpretation. The query processing and execution block then guides the robot's real-time actions. Together, these components enable the Robo-CSK-Organizer to perform complex tasks with high accuracy, explainability, and adaptability. At the core of the Robo-CSK-Organizer is the integration of common sense knowledge, which enhances the system's decision-making. CSK includes everyday knowledge that humans intuitively use, like knowing that an apple belongs in the kitchen, not the bedroom, knowledge that AI systems typically lack. To bridge this gap, we use ConceptNet, a large-scale knowledge base that helps Robo-CSK-Organizer understand the relationship between objects and their typical context. For instance, ConceptNet guides the system in understanding not just what an object is, but where it is usually found and how it relates to other objects. By leveraging CSK through ConceptNet, our system makes more informed, nuanced, and contextually appropriate decisions. This integration moves beyond the limitations of traditional AI, which often makes opaque decisions by making the process transparent and explainable. Ultimately, the use of CSK and ConceptNet enables the Robo-CSK-Organizer to perform complex tasks in a way that mirrors human common sense reasoning. This slide illustrates how the Robo-CSK-Organizer uses ConceptNet to determine the appropriate placement of objects, such as pair, within a specific context like kitchen. The diagram shows the relationships between different objects and locations, which are represented as nodes connected by edges labeled with types of relationships, such as at location or related to. To determine that a pair belongs in the kitchen, the robot follows a logical pathway through these relationships. Starting from the pair, ConceptNet identifies that it is related to the concept of apple. This apple category is in turn related to food, which is typically found in kitchens. The system then examines the strength of these connections or the weights associated with these relationships. For instance, the pair is strongly related to apples and fruits, which are generally found in the kitchen. The robot uses this knowledge to determine that the most appropriate place for the pair is the kitchen. This process highlights the power of common sense reasoning in Robo-CSK-Organizer. By navigating through these interconnected concepts, the system is able to make informed decisions about where the object should be placed, mimicking human-like understanding and ensuring that the decisions are both logical and contextually appropriate. Later on in the video demo that we shall demonstrate at the end of this presentation, you will get to see this more in action. This highlights three components of the Robo-CSK-Organizer: DETIC, BLIP, and the Franca-Amica arm, each crucial to the system's functionality. DETIC is our object detection module, expanding the vocabulary of detectable objects to tens of thousands, ensuring comprehensive detection for diverse tasks. BLIP, or bootstrapping language image pre-training, enhances vision language tasks by generating synthetic captions, enabling the system to interpret scenes more like a human, integrating both visual and textual data for informed decisions. The Franca-Amica arm, equipped with Intel RealSense 3D infrared camera, manipulates objects with precision and adaptability, executing decisions made by the Robo-CSK-Organizer accurately. Together, these components form the backbone of our system, enabling it to perform complex tasks in dynamic environments with precision and explainability. The architecture of the Robo-CSK-Organizer integrates advanced components for intelligent and explainable decision-making. BLIP handles context recognition, processing visual and language data, while DETIC manages object detection. These components feed into the query processing and execution module, guiding task execution. The Franca-Amica robotic arm and Intel RealSense dev camera execute physical tasks and capture visual data. The system's actions are coordinated through the robot operating systems for seamless integration. ConceptNet provides common sense reasoning, enabling the robot to make adaptive, contextually appropriate, and explainable decisions. Together, these components deliver precise and transparent actions in dynamic environments. The Robo-CSK-Organizer uses a systematic algorithm to sort objects into appropriate context through video feed analysis, object detection, and common sense reasoning. For the first step, the video feed input, the system begins by receiving real-time visual data via video feed. Step 2, context recognition. Using BLIP, the system recognizes the environment's context, for example, the kitchen or the office. Then there's the object detection. DETIC then detects and labels objects within the video's frames. Afterwards, now we retrieve the common sense knowledge. The system queries ConceptNet for contextual information about the objects, guiding the sorting process. Then it's the decision making. Decisions are made based on the retrieved knowledge, ensuring logical and contextually appropriate sorting. Finally, it's the output, or the sorting of the objects. Finally, the system places the objects into context bins, displaying the results as an annotated frame from the video feed. The algorithm is key to the Robo-CSK-Organizer's ability to perform complex tasks with accuracy and explainability, mimicking human-like reasoning in its decision-making. In our experimental setup, we chose to compare the Robo-CSK-Organizer with a ChatGPT guided organizer to assess how the integration of common sense knowledge enhances AI applications in organizing objects in domestic environments. The primary focus of this comparison is on several key factors: in the ambiguity resolution, consistency, task relevance, adaptability, and explainability. By analyzing how each system handles these challenges, we aim to highlight the strengths and weaknesses of both approaches. The Robo-CSK-Organizer leverages a structured common sense knowledge base through ConceptNet, enabling it to make decisions that are not only accurate, but also contextually grounded and explainable. In contrast, the ChatGPT guided organizer uses a language model to guide its decisions, which offers a different approach to handling ambiguity and adaptability. This comparison underscores the importance of explainable AI, especially in environments where transparency and reliability are critical. Through this evaluation, we aim to demonstrate the added value of integrating CSK into AI systems, providing clear insights into the decision-making processes and ultimately improving their effectiveness in real-world applications. In evaluating the Robo-CSK-Organizer, we focus on 4 key metrics: ambiguity, consistency, adaptability, and explainability. Ambiguity measures the system's ability to resolve scenarios where an object could belong to multiple contexts, critical for decision-making under uncertainty. Consistency assesses how reliably the system places the same object in the same context under identical conditions, indicating stability. Adaptability evaluates how well the system adjusts its placement strategy to changing task priorities, reflecting flexibility. Explainability gauges how easily users can understand the system's decision, highlighting transparency. These metrics provide a comprehensive assessment of the system's strengths and areas for improvement. In this slide, we see how the Robo-CSK-Organizer approached the task of organizing a pair of scissors. By leveraging its integration with ConceptNet, the system utilized Commonsense Knowledge to navigate the decision-making process. The Robo-CSK-Organizer analyzed the connections and weights within ConceptNet to determine the most appropriate location for the scissors. Specifically, the system considered the relationships such as at location and the degrees of separation between the scissors and potential contexts like the dining room. By evaluating these factors and prioritizing paths with higher semantic relevance and stronger associations, the Robo-CSK-Organizer not only concluded that the dining room was the most contextually appropriate location for the scissors, but it was able to explain this decision as well. In contrast, this slide illustrates how the ChatGPT guided organizer approached the same task. Lacking access to structured common sense knowledge, the system placed the scissors in the child's playroom. This decision exposes a significant limitation of relying solely on a language model without integrating a knowledge base like ConceptNet. The choice made by the ChatGPT guided organizer is not only opaque and impractical, but also potentially dangerous as it overlooks critical safety considerations. This comparison underscores the importance of incorporating common sense reasoning into AI systems to ensure they make decisions that are both intelligent, safe, and explainable. In this slide, we compare the consistency of the Robo-CSK-Organizer and the ChatGPT guided organizer across various objects. The results indicate a significant difference in performance between the two systems. The Robo-CSK-Organizer demonstrated 100% consistency in sorting objects across all trials, regardless of the object type. This consistency is attributed to the use of ConceptNet, which provides stable and repeatable knowledge through its structured common sense reasoning, ensuring that the same context is selected for an object every time. On the other hand, the ChatGPT guided organizer exhibited less consistency, particularly with objects such as adhesive tape, belt, sock, remote control, and aerosol can. The variability in ChatGPT's performance can be attributed to its reliance on pre-trained patterns and deep learning models, which do not inherently ensure consistent decision-making in systematic object organization tasks. These results underscore the robustness of the Robo-CSK-Organizer in delivering consistent outputs, making it a more reliable choice for tasks requiring stable and predictable behavior in object sorting. In conclusion, our project, the Robo-CSK-Organizer, demonstrates significant advancements in the integration of common sense knowledge with AI systems by utilizing ConceptNet. We have successfully blended structured knowledge bases with machine learning, leading to enhanced decision-making, transparency, and accuracy. This enables the system to perform operations that are intuitive and contextually appropriate. The Robo-CSK-Organizer also shown superior consistency and adaptability, achieving a 100% consistency rate in object sorting tasks. This level of reliability not only ensures user trust and predictability, but also showcases the system's exceptional adaptability to context-specific directives, making it ideal for dynamic environments and next-generation multi-purpose robots. Moreover, our work contributes to advancements in explainable AI by providing clear and logical paths for decision-making. The Robo-CSK-Organizer sets a new standard for explainability in AI and robotics. This transparency is crucial for fostering better collaboration between humans and robots, ultimately paving the way for more effective and trustworthy AI systems. The Commonsense Knowledge Project thrived on a research visit by Dr. Parno Varde at the Max Planck Institute for Informatics at Saarbrücken, Germany, with further work at Montclair. This work is supported in part by the National Science Foundation. Our experiments are conducted in the Cross Lab at Montclair, of which Dr. Wei-Tian Wang is the director. We also thank CSAC at Montclair, of which Dr. Parno Varde is an associate director. Now, please allow me to show you a brief video demonstrating our project at work.
First, we'll discuss learning task context. As you can see on our experimental area, there are 4 bins, each containing a room image. From left to right, they represent the bedroom. kitchen, garden, and office. A robot scans each bin, identifies the room using BLIP, and logs the room names with their respective coordinates. In the video's upper right, you'll see the robot's perspective as it identifies and learns each context. We have also increased the video speed to 3 times for brevity and convenience. Here we have our 4 contexts for better viewing. On the upper left is our garden, on the upper right is the kitchen, on the bottom left is the bedroom, and on the bottom right is the office. Now onto object recognition and sorting using Commonsense Knowledge. Here we have 3 objects on our experimental area. From left to right we have a pair, a remote control, and a computer mouse. Our Robo-CSK-Organizer employs the Tektron tool to recognize and pinpoint each object, then places them in their most relevant context based on the most optimal ConceptNet path. In this case, by using Commonsense Knowledge from ConceptNet, our robot was able to deduce that the most likely location for computer mouse is in the office. The most likely location for remote control is in a bedroom, and the most likely location for a pair is in the kitchen. Here's a visual representation of ConceptNet, showing how the kitchen relates to our 3 objects. Using ConceptNet, the pair was categorized under the kitchen. Let me explain this visually. Starting with the kitchen node, the pair node is to its left. We explore the 3 left nodes, prioritizing the highest weight of the at location edge, leading us down the leftmost path with a weight of 7.21. This path indicates that food is typically found in the kitchen. Further down, apple is linked to food by a related to edge. And then apple is connected to pear by another related to edge. Thus, following this logic, a Robo-CSK detector placed the pear in the kitchen. Following this entire path, we see that food is at the kitchen, food is related to apple, and apple is then related to pear. Thank you very much for your time and consideration.